In this video, we're going to be looking at how to calculate the pH of an acid. So you may have come across this equation, pH equals minus log to the base 10 of H plus ion concentration. So if you were to rearrange this, you would get H plus ion concentration is equal to 10 to the minus pH. So that's what this log to the base 10 means. So if you were to have a strong acid, for example, we could have HCl, then the method for working out the pH of the acid is quite straightforward. All of the acid is going to be dissociated into H plus and Cl minus. So if, let's say, we have an initial concentration of HCl of 0.1 moles per decimeter cubed, then all of that is dissociated, so our concentration of H plus ions is also going to be 0.1 moles per decimeter cubed. Now all we have to do is put that value into our pH equation. So pH equals minus log to base 10 of H plus ion concentration, which is going to be 0.1. And if we put that into a calculator, we get the answer 1. So a 0.1 mole per decimeter cubed solution of HCl will have a pH of 1. But what about a weak acid? So let's say this time we've got a weak acid. So as an example, let's say we've got some ethanoic acid. So this time, because it's a weak acid, not all of the acid is going to be dissociated. So we've got an equilibrium like this. Now the extent to which the acid is dissociated here will depend on the Ka value. So Ka is just your equilibrium constant for an acid. So in this case, we're going to have the concentrations of our products over the concentrations of our reactants, like this. And let's say we get given the Ka value for ethanoic acid, which is 1.7 times 10 to the minus 5, and the units would be moles per decimeter cubed. And let's say we get given the concentration of ethanoic acid, and that is going to be 0.1 moles per decimeter cubed. Now we can use this value and our value for Ka to work out the concentration of H plus ions. Now you might notice we haven't been given a value for the CH3COO- anion. So what can we do about that? Well, for every H plus ion that you have, you're going to have one CH3COO- ion, because both come from the same molecule CH3COOH. What this means is that you can say your H plus ion concentration is going to be the same as your CH3COO- concentration. So let's substitute that into our Ka equation, which was this. So we just said that we can swap out this for H plus. So that becomes Ka equals H plus squared over CH3COOH. And if we rearrange this equation, we get H plus ion concentration is equal to the square root of our Ka times the ethanoic acid concentration. Then putting in our values from before, we would have 1.7 times 10 to the minus 5 for Ka, times by 0.1 moles per decimeter cubed for the concentration of ethanoic acid. And if we put that into the calculator, we get 1.3038 times 10 to the minus 3 moles per decimeter cubed. So then the final step would be to put this into our pH equation, like this. And that comes to 2.88. And if we compare this with the pH of 1 that we had for the hydrochloric acid, you can see that the hydrochloric acid at the same concentration will be more acidic than the ethanoic acid, which is what we'd expect given that the hydrochloric acid is a stronger acid. So to summarise this, we have two options for calculating the pH of an acid. Either it's a strong acid, and you can just assume that the concentration of the acid will be the same as the concentration of the H+ ions, and then all you have to do is put that into your pH equation. Or you've got a weak acid where you first need to use Ka to find your H+ ion concentration. So that's where your H+ ion concentration is equal to the square root of Ka times the acid concentration, and then use your pH equation to find the pH from the concentration of the H+. If you found this video helpful, please like and subscribe. I'll be posting more videos about acids and buffers soon.